Hello, all. Welcome to this second part of our Pytorch tutorial. Now, earlier part of our Pytorch tutorial, in which we understood the idea of tensors and what are the attributes of the tensors, how do you create tensors, what are the operations that you can perform on the tensor, and we understood the loading of datasets. Okay, so now we have loaded the dataset. Now let's try to write the code for a neural network. Okay, now here in this particular tutorial, now I'll be restricting myself to the MLP. Okay, now in the coming tutorials, we will be looking at CNNs, but in this specific tutorial, my concentration is on creating an MLP. The structure of the MLP that I have considered is like this. Uh, See, my data set that I have in consideration is MNest. Okay, the data set under consideration is MNest. So now each class, so now our Y now belongs to 0 to 9. Okay, now that means that the output now which is there should be a probability vector now of length 10. Okay, now how do we do it? Now we pass it through a softmax function. All of you know that, but in terms of the structure of MLP, now one thing is sure, that my output, now this which I have now, this belongs to, this is a vector in R10. Okay, but this is not a probability vector. Okay, I have to convert this into a probability vector. Now, how do we do it? Now we pass it through a softmax function, and then comes a probability vector, let's say P, now wherein which you have P0 till P9. Okay, now this will be the vector that you get. And then what does this indicate? Now this is the probability that y is equal to 0 given the input x. That is what this term indicate. And this is probability y is equal to 9 now given x is what it means. And then when you sum up all these elements, now you should get to 1. Okay, and each of them should be uh, what do you call, non-negative. Now all those properties should be there, but my whole point is the output now should be having 10 nodes here. Okay, now since I'm going ahead with an MLP, okay, now how should my input look like? Now the input for this MNest is 28 cross 28. Okay, this is a matrix. Okay, it's a 28 cross 28 matrix. So now now, since we want to use an MLP, now if I want to use an MLP, now this I have to convert it. I perform a raster scan and then convert it into vector, which is 784 cross 1, 28 cross 28. Okay, if you multiply it as 784 cross 1, I convert it into vector. Now, therefore, now what happens is my input, okay, my input will be a, so this actually belongs to R784. Okay, now then you have to make choices. Now, how many hidden layers now I should have? Okay, so and then what should be their dimensions? Okay, now all those things. Now I will make a very simple case now, wherein which I have two hidden nodes. Now each of them belongs to R 512. Okay, the output belongs to R512. Now that means that I have 512 nodes here. The output of this layer will be a vector in R512. Now that's what I mean by this thing. Now that means that now I have, this is one matrix, this is another matrix, this is another matrix. Now let's call this as W1, W2 and W3. Now this will be, okay, this belongs to our 784 cross 512. Okay, now there will be bias term for each of those neurons. I'm not going ahead and considering it. Okay, now just for ease of computation, this is our 512 cross 512, and this belongs to our 512 cross 10. Okay, now this is W1, W2, and W3 matrix. Okay, now how will the forward propagation happens in this case? Now you have an X, now which is 784 cross 1. Okay, now you have this, we will have W1 transpose X. To that you pass through a non-linearity. Okay, that you have W2 transpose, that you again pass through one more non-linearity, and then that you multiply again, you have W3 transpose. This you pass through the softmax. Okay, this is how it will be. Now let's try to get this. Now this, what is the size of this? Now this is W1 transpose. Now W1 is 784 512. Now this is now 512 cross 784. This into 784 cross 1. Therefore, this whole thing will be 512 cross 1. Okay. And then you apply element wise non-linearity. Okay. Now, whatever non-linearity that you want, sigmoid, ReLU, or whatever. Okay. And then you go to the next one. The next one is 512 cross 512. Now you take the, and this is 512 cross 1. Therefore, the output that you get is 512 cross 1. This is the, once you apply this, you get a 512 length vector, and then you apply this matrix, again you get a 512 length vector. Okay, and then you pass it through this, the third one. Now this is, if you take the transpose, it is 10 cross 512 into 512 cross 1. Now this will be a 10 cross 1 vector, and then you pass it through the softmax. Now once you pass it through the softmax, you get this probability vector, where in which this is P0 till P9. Now please excuse me for using the abuse of notation. Now whenever I mean P0 here, now what do I mean by this is Py is equal to 0 conditioned on the given X. Okay, now that is what I mean by this. This is the probability vector that you get post passing through the softmax function. Okay, so this is the full structure of the MLP that I'm considering. Okay, now first, what am I supposed to do? Now first I have an image. Now first I should flatten it up, and then perform the series of matrix multiplications, and then get a vector. Now the output of this point is what is known as a logit. Okay, now you have this, and then you pass it through a softmax method. The output is what is known as a probability vector, or it is also known as posterior, which totally makes sense. Okay, this is a posterior. Okay, so now this is the structure of the network that I am considering. Now let's try to code it up. Okay, and then we will be doing it so on a device. We will be doing it on a GPU device. Okay, so now let's do it. Okay, now the first thing that I should do is first I should import all these methods. Okay, before that, runtime, runtime. Now here, go to this runtime, and then you can see change runtime here. Now please select the GPU. Okay. Now then the current runtime will be disconnected. That means that whatever you have stored in your working directory will be erased. Now we have to rerun the data loader. Okay. Please remember that. Okay. So this is for collab. Okay. Now that is not the same case whenever you are having a physical device with you. Okay. Now I have enabled the the CUDA device, and then the same thing is replicated here at the bottom right corner. You're using a T4 GPU. Okay. So now you need to, what are the things that you want? You want OS. Okay. Now import torch is needed. Now from torch, import NN. NN stands for neural network. Okay. You use this NN. So and then so these are the three things that are needed. Okay. I'll run this. Okay. Now then I have to use the device. Now I have to use now CUDA. If CUDA dot is available, now this is the Boolean outcome. Now if it is available, then the CUDA will be considered. If it is not available, now we will consider the CPU. Now I'll rerun it. Now using the CUDA device. Okay. That means that as of now, I'm using the GPU which is there. Now I have to rerun this whole data loader. No, because it would have erased the previous case. So I'm just rerunning it so that I have my data loader ready with me. Okay. So now let's go ahead. Okay. Now I have to create the neural network. Now you have to create a class for this. Okay. Now class, let's say neural network. Okay. Now that has to be a child of this nn dot module. Okay. Now, because whenever you are creating, what do you mean by creation of neural network? That means that you are having a couple of weights and biases, correct? Now, that means that those weights and biases has to be initialized. And then for those weights and biases, you have to perform the backpropagation. So you have to update the weights. Now, all these methods, you don't need to explicitly code them. Now, these are already present in this nn dot module. You just need to inherit it directly. Okay. Therefore, we have to create it as a child of nn dot module. Okay. And then we have to define the init method. Okay. Now, yeah. If you write it, it will start autofilling things. So you use the super, that is, you're calling the init method. Calling the super, that means you're trying to access the parent. Now you're trying to call in the init method. Now I have to pass the name of the class. The first thing that you should do is, now first you should flatten. Now that means that you have to convert your matrix, which is a 28 cross 28, into a vector. Now that is what you're doing. Self dot flatten, nn dot flatten. Here you're just initializing things. You have not yet come to the thing. Okay. Now then comes the important thing. Now, if we understand from here, now post flattening, once I give the input, now this you can consider it as one operation. No, you can consider this whole thing as one operation. I give the input and then I get the output. Think of it like that. Because the input is here, the output of this operation will be given as input to this. The output of this operation will be given as input to this. Now I can think of this as one whole conveyor belt kind of a thing. I can think of it as a stack of operations. Okay. Now this neural networks allows us to create stacks like this. Okay. Whenever you have the series operations, that means that there is no branching, conditional branching that is involved. Now you can always have this series operations put together. That is what is known as stacking. Okay, that is done now using this idea known as nn dot sequential. Okay, now let's create that. Now self dot so linear ReLU stack. Okay, this is the variable name that I'm using. Now linear is I have all these MLPs. Now ReLU is the nonlinearity that I'm using is the ReLU. Now you can use other non-linearities like sigmoid or tan H. Now sigmoid and tan H are preferably, these are all empirical ideas. Now whenever you're doing image work, working on images, preferably we use ReLU. Okay, and whenever we are dealing with sequences, that is when we use sigmoid and tan H. Okay, now there is no proof for it. These are empirically evolved ideas. Okay, so nn dot sequential. Okay, now the first thing that you should declare is post flattening. Now you have to declare this. Okay, now this is a linear layer, nn dot linear. The input is 28 cross 28, which is 784 cross 512. Now that means that you have created this matrix. Okay, and then after this, what is that you have supposed to do? After the application, you have to use the ReLU, which makes total sense. The output of this post this transformation, you have to apply the ReLU here. That is what this nn dot ReLU means. Now then you have again nn dot linear 512 cross 512, and then you have ReLU, and then 512 cross 10. Okay, now you have initialized all these three matrices, W1, W2, and W3. Okay, now please don't confuse with, see, it has two hidden layers. Okay, no, but the way in which we are initializing is with respect to this matrices. Each matrix is initialized with one nn dot linear. Now please remember that. Okay, so now, and then the nonlinearity that you are using is nn dot ReLU, the ReLU nonlinearity. Now there is no hard and fast rule that whatever nonlinearity you have used here, the same one you have to use here. No, you can always mix and match. See, all as sir told, no, these are Lego blocks. Now think of them like that. These are Lego blocks. No, you can mix and match them, but the compatibility with respect to the size should be there. Okay, that's all is the requirement. Okay, now you have declared this. Now your init method is done. Now you have to define the forward process. Okay, so now in the forward process has to be defined. That is the forward pass. Okay, no, but you don't need to specify the backprop. No, it has what is known as it will create what is known as a directed acyclic graph, which we shall look next in this tutorial. Okay, when which things are taken care, so you don't need to worry about it. Okay, so now you have to create this forward method exactly with the same name, where the instance is the first argument. By default it is there, and then the input which is there is the second argument. Now first you flatten it. Okay, now then you get logits equals self.linear stack ReLU. Now if you understand this, first you get an input, first you flatten it up in this place, and then you give it here. This whole thing is 1. You will pass this, and then you get the logits. Okay, now that is what is happening. Now this is the forward method that you have to have. Okay, so now you have defined the class, and then now how do you create an instance? Now you have to create a model, some variable to store it. So now that you'll use neural network, and then you have to port it. See, whenever you create an instance, it will be there on the CPU. Now you have to port it to the GPU. How do you do it? To device. Okay, now you have it. Now device is CUDA device. Now you will be porting it onto the GPU. Okay, so now whenever you perform any operation, now the model is on GPU. Now all your data should be on GPU itself to perform the operations, and the output will also be on the GPU. Okay, now then you can print the model here. Okay. Here you can see that the input is 784, and then 512. Now bias is true. That means that for each of the output neuron of 512, you'll have a bias. So in total, the bias will be 512, 512, 10. Okay, 1024 and 1034. Okay, that will be the number of biases, and the number of weights you can compute. Okay, now that is 784 into 512 plus 512 into 512 plus 512 into 10 plus 1034. That is the number of weights that you have to optimize here. Okay. So now that means that in such a huge dimension, plus one, that is the loss curve, and then you have to perform your empirical risk minimization over the loss surface in such a huge dimension. Okay. So now let's take an input. Let's take X. I'll create a dummy input. Okay. Torch dot random. I can specify the size 1 comma 28 comma 28. Okay. Now and then what is the device? The device that I want to put it here. Device is the argument. Now for that I'm putting the value which is the same name, same variable has been obtained. So logits equals model of X. Okay. So and then let's print this logits. Okay. Now whenever I say model of X, now the forward method will be called. So your forward method will be applied. Now this 28 cross 28 will be first converted into a vector of say 784, and then it will be passed through this whole thing. Now you can see this. Now, this is the logits that you have got. Okay. Now this logits which is there has to be converted into the probability vector. Now spread probability. Now how do I do it? I use the softmax function. Now how do I do it? Nn dot softmax. Okay. Now dimension one. That means across the column you get it. Okay. Now and then you print this prediction probability that you have. Okay. Now you can see this. This is randomly initialized. So the only thing that I'm trying to say is now the propagation, the forward propagation is happening without any mismatch in terms of size. Okay, learning is not happening as of now. I'm just saying that the forward propagation which is there is happening without any issues of mismatch. Okay, now this is my probability vector. Now, how do I choose the class? How do I make the decision? Now, I have to take the argmax of this. Okay, the index, now where which the maximum value is there, that is the value, my y prediction equals the argmax, the first argmax of this, and then I'll be printing. Now, the predicted class is 2. Now, as you can see, it is on the device. Now, because model is on the device, input is on device, everything is happening on the device. Now, please remember that. Okay, fine. Now, is this clear? Any questions on this? Oh, sorry, it's not question. Okay, I thought this is what happens. Normally, we teach in the class, and then we say that any questions. Oh, I actually forgot that I'm live recording this in front of a system. Okay, so yeah, we can actually print these things. Okay, uh, so we can obtain some values. Wait a minute. Okay. So now let's see how the ReLU is working. Okay, just to show you that how the ReLU works. Okay, now I'll just have just create layer one, which is nn dot linear. Okay, in features is 28, and then you have some x dot. I have to first flatten it up, right? Okay. So wait. Okay. Nn dot nn dot flatten of the x that I have. Okay. Print then one. Okay, there is some error. Let me do this then. Flatten equals an n dot flatten. Just flatten of x. Oh, again. Okay. Okay. What is the size of this x? Is 128.28. Let's do one thing at a time. Let's first flatten it up. So now flatten equals an n dot flatten. Okay, yes, fine. Now I'm getting 784. Okay, then layer 1, image input hidden 1. Okay, it's not on the device. Yeah, this layer 1 has to be ported onto device. That's all. These are the common mistakes that happen. Okay, yeah. So, see, whenever something is created, as I told you, it will be on the CPU. You have to explicitly port it. Now you can see that. Now this is what happens. Now you get a vector like this. Now what will happen when I apply the ReLU? Okay. So now C equals nn dot ReLU of hidden 1. Now as you can see here, now ReLU is max of 0 comma each element. Okay, now that means that all the negative values which are there will be converted to 0, and you can see it here. This is how the ReLU operation actually happens. Okay, so yeah, parameters, yeah, we saw it here. Good. Okay, now this is how actually a neural network works. Now till now whatever we have seen is just the forward propagation. See, we haven't seen yet the back propagation. Now we'll be just seeing it as a sample case for one operation, and then that we can extend it for the whole MLP. Okay, just to understand now how does this work. Okay, so now what we shall do is now we shall create a very small operation to understand the whole thing. Okay. Now let's say that I have my input x. Okay. This input x, I'm multiplying that with this w, and then post multiplication, I'm adding this b. Okay. This is what I'm calling it as z, and then I'll apply a loss function. Now let's say that I'll apply the cross entropy over the logits. Okay. Now for that cross entropy to apply, I have to supply y to this. That will give the loss. Correct. Now what is happening is now I have wx plus b is your output. This is your z. Okay. And then what you are trying to do is, now we are compute the C loss with z and y. Now this is the operation that we are performing, and then it is very much evident from here. Now these are the parameters that we want to learn. Okay. So now let's try to understand for this simple case. Now how does the back propagation works? How does the gradients are obtained for this particular simple case? And then now this is nothing but for one neuron, and then you can extend it up for the further cases. Okay. I'm just trying to understand with one specific cell. Okay. So now this is we are dealing with the automatic differentiation. So now the go-to algorithm is backpropagation as of now, unless someone comes up with one good algorithm which can actually replace backpropagation. Till that point, we'll be using the backpropagation. Now let's take x. Now x, let's say that it's torch dot ones of size 5. Okay, and this is our input tensor. Okay, and what will be my y? My y will be torch dot zeros of size 3. This is the expected output, and then we have w. Now w now has to transform from 5 to 3, right? So it has to be a matrix of size 5 cross 3. Okay, and then you take w transpose x. Okay, and then you have to obtain the gradients. So now we use this requires grad is equal to true, now which will take care of what is known as a computational graph. Okay, now this is a built-in differentiation engine that is used in what is known as AutoGrad. Now it supports the automatic computations of gradients by any of these computational graphs. Okay, so now w and b you have, and then what will be the value of z? Z will be the multiplication of x and w plus b, and then what will be the loss? The loss you have to compute, which is n dot functional binary cross entropy with logits. Okay, z and y. Now this is the loss that you're using. Okay, now you got something. Now let's see what are these. Okay, so now what happens is each of this now will have what is known as a gradient function. Okay, which is known as the grad function. Okay, now wherein which we compute its derivative during the backward propagation step. Okay, and then it is stored in this grad function. So now let's print and see now how are the gradients stored. Now I'll use the formatting f. Now you can see this. Now it is stored in this grad function in these locations. Okay, now how do we compute the gradients? Okay, now you have to use now what is known as loss dot backward to obtain the gradients. Okay, this is the back propagation. Now for that, what it will do is, now with respect to the loss, now it will be computing the gradients for w and b. Okay, you'll be obtaining the partial derivatives now with respect to the parameters of the loss. Okay, so now x and y are fixed, so it doesn't make any sense. No. to go ahead with that. So we can look at now what is the grad value. Okay. So now how do we do it? Once we do it, now we have this print w.grad grad, it will be there. Now you can see that this is the gradient value. Now it is very much evident that, see, the gradient value and the value should be same. Now otherwise, now how do you perform the stochastic gradient descent equation, now, which is when which w minus alpha times the gradient. Okay, now alpha is a fixed value. Now you will be going ahead. This is how you obtain the gradients. Okay, so now whenever you have a larger network in picture, now it is not needed that for every parameter, okay, you need gradients, and every time you need to compute the gradients. Okay, now the gradient computation now can be disabled in certain cases. Now one is during your inference. Okay, now during your inference you don't need to keep track of any of the gradients, correct? No, gradient should be taken with respect to what you don't. I'm not saying about computation. I'm saying about tracking. Tracking of gradient itself can be disabled. Okay. So now, uh, how do we know that? Now let's do that. Now we just obtained z, right? Now z equals, again. Let me compute torch dot. So it is matmul of x comma w, and then you can say that z dot requires grad. Now this will be a Boolean value. It is true. Now that means that as of now you are enabled the gradient tracking. Okay, but on the other hand, now we can disable this. How do you disable this? With torch dot no grad. Now whatever operations you do now, for this outcome which is there, no, you are not tracking the gradients. Now because the operation has happened, wherein which I'm saying that I don't need any of the gradient tracking. Okay. Now, therefore, for certain operations, you can actually disable the gradient tracking and then work with it. Correct. This is one way. The another way is using what is known as detach. Okay. Using, if I compute this, okay. Now, let's say that I just copy it, z determinant just equals z dot detach. Okay. So now, if you put, now what is the gradient of this? This is false. Dot detach will also exactly do the same thing. Okay, the same result that we have obtained earlier, it is just doing the same thing. Now then what happened to z's gradient? Okay, that also we can track. Print z dot requires grad. Yeah, that will be true. Now because you have detached it for this specific case, okay, this variable is not holding any of the gradient tracking. Okay, fine. Z still has the gradient tracking, but Z det doesn't have the gradient tracking. Okay. Now, why is this needed? See, sometimes whenever we are having a huge network, we would have frozen couple of parameters and only want to update the weights of certain other parameters. Now, in those cases, for those parameters, you don't need to track the gradients. Okay. In those case times, you can actually say that, no, I don't need it. I don't need to keep track of the gradients in these cases. Now, all these are achieved with what is known as computational graphs. Okay. Now, how does it do is this autograd which is there, it will keep the record of the data of all the executed operations along the new tensors that have obtained. Okay. And how does it do that? It does it with what is known as a directed acyclic graph. Okay. Now, this is similar to the graph that I actually wrote. The one that okay, I'll just show you. Wait. This is the directed acyclic graph. Okay. It is stored like this. Okay. Now, then what happens in this DAG? Now we will leave the input tensors now which are having a path from input tensors now roots to the output tensors. Now this will so by tracing this graph from root to leaves, now we can automatically compute the gradients. Okay. Now in the forward pass, now the autograd now which is there will simultaneously perform two things. Okay, in the forward pass. Okay. Now run the operation which is there. Okay, and maintain the operations as per the DAG. Okay, it will maintain the gradient function as per the DAG. Now once you perform the backward option, okay, now it is called on the DAG root which is there, and autograd, then what does it do? Now it will compute the gradients on each of the value now using the gradient function. Okay, and accumulates the respective gradients with respect to grad. So and then how does it do it? It uses it now the chain rule, the standard chain rule, which is hard coded. Okay, now this chain rule propagates all the way to the leaf nodes. Okay, now this is where this is the grad, this is the grad function. Okay, now compute the gradients for each of this grad function wherever it is needed, and they're accumulated at these points. Okay, now that is how it actually computes the gradients. Okay, so now the key takeaway is not every parameters needs the gradient update. So now depending on the need, now you can actually now freeze a couple of things. Okay, and all these gradient operation I did on CPU. I haven't ported any of these onto GPU, as you would have noticed. Okay, now with this we conclude this second part of the tutorial in which we actually wrote the first neural network, and then we did the forward propagation till prediction also. So we converted the logits into the posterior probability, and then we obtained the prediction as well. And then for a very simple case, we understood how does we can play with gradients. So in the next part of the tutorial, we will be seeing how to optimize the weights of these new things, and then how does the whole training process works, and then how do you save the model. Okay, this is what we'll be seeing in the next part of the tutorial. Thank you all for watching. We will meet in the next tutorials.